Okay, so if you remember in chapter 8, we say that if you apply a certain stress that is higher than the yield strength of the material, then you will move from elastic region to the plastic region. And I hope that you still remember that the difference between the two is the plastic deformation. Whatever deformation you have in the material is something permanent, something that will exist, will change the dimension of the material, that will stay with the material even if you remove the external forces. Over in the elastic region, whatever deformation you have, it's something temporary. So whenever you remove the force, whether it gets back to its original dimension directly, or it might be time dependent. So it will have an inelastic behavior. But the difference is plastic and elastic is the plastic is permanent. But then we try to answer the question of why this is happening, why we have elastic deformation, what's happening internally. Can we connect between what's happening internally and what we see from outside? And it turned out during the elastic deformation, we are stretching the bond between the atoms. So once you remove the load, what's going to happen? The atom going to get back to their original position. And we call that position the equilibrium interatomic spacing between the two atoms. And if you apply a stress that is higher than sigma y, it's called the yield strength. If you apply a stress that is higher than the yield strength, then what's going to happen, you start to get into the plastic deformation. So what we will do in chapter 9, we will try to give more explanation why the material start to have plastic deformation. And we'll try to connect this to with the dislocation motion. So the definition of plastic deformation, it is not the movement of dislocation. It is the large movement of dislocation. So in order to initiate the plastic deformation, you need to move large number of dislocation inside the material. Okay, so we will be talking about this in more details in chapter 9. And then we will see that how the dislocation can be correlated with the strength of the material. Because that will allow you to design a material that might have extra strength on it, or maybe it's more ductile. So we will be talking about this, inshallah, in next chapter. What are possible mechanisms to make the material, for example, more stronger? Okay, great. And now let me go to the chapter 9. And if you notice, the chapter is called the dislocation, and it's called the dislocations and strengthening mechanisms. Okay, this is a very important chapter because it involves some way of designing a material. Okay, great. Now let me take you to this figure. And I would like to ask you a question. If you look at this figure, do you notice any difference between different regions inside this part? Do you see any differences between this region, this region, this region, or this region? Do you notice anything here that is different, that is weird than what you expect?
I see each dislocation.
What?
We can see each dislocation.
Edge dislocation, okay? You see edge dislocation that is located here at this point. Okay, great. So what do you see else? What else do you see?
The sides.
The what?
The sides of the unit has been shrunk.
The size of the unit?
The sides.
The side of the unit
yes.
being shrink here but you have more in this region. Okay, right? This is what you meant?
Yes.
Okay. Okay. Else? What else? Let's get some more answers. Do you see any differences when you look at the atom positions as you look here at this part?
It's kind of going in a narrow direction. It's compressing.
You see what again?
It's not narrowing down. And it's
Narrowing
kind of
down. Okay. Okay. Is it narrowing down here?
no, just in some parts in the below part.
Okay, some parts. Okay. Do you see anything, if you want to look at this region and you compare it to this region, do you see any difference between this region and this region?
Maybe the second region has more energy.
The edge dislocation is at a different position.
Okay, okay. So you have here edge dislocation. What we can say, the difference between this region and this region, you have extra half plane of atom, right? That's not connected to the bottom. So you have something missing here, right? Compared to this region, we have, let's say, plane D. It will start from the top to go all the way to the bottom, right? C start from the top, go all the way to the bottom, right? Now, if you go to A, you start from the top and then it will end here. So you have some discontinuity, right? Okay, what else? If you look then around the dislocation, what do you see if you consider the atomic position? If you have a perfect material and you have this kind of material, what you can comment about the atom position?
Do you mean that there is dislocation?
There is a dislocation here, right? So in perfect crystal, what do you expect, Yasami? What do you expect to see? You expect to see atoms lying underneath each other,
yeah,
in a vertical
yes.
way and also in the horizontal way, right? You have atoms, we're talking about metals here, right? So atoms lying next to each other in a horizontal and also in a vertical way, right? Now,
arrange lattice points.
Right? Again?
Arrange lattice points.
Arrange lattice point is what you expect in the perfect crystal, right? Now, what do you see here in terms of the atom positions? Do you think the atoms around this region are in their equilibrium position, or you think they are shifted?
No, shifted.
Shifted, right? So if you want to compare what's happening around the dislocation in such crystalline with the perfect crystal material, you can see clearly that the crystal material, the atoms, are positioned in their equilibrium position that can guarantee equilibrium interatomic spacing between the atom and its neighbors, right? So what's going to happen if you shift those atoms or push those atoms from their original position? What do you think going to happen to the system, to the energy of the material?
It will increase.
It will increase. Wonderful. Because if you remember, we said earlier that, if you push the atoms away from each other, right, you're increasing the energy of the system. If you bring them closer to each other, also you're going to increase the energy of the system. There is only a certain region where the energy of the system will have a minimum value, right? So if you shift the atom or you push the atom from their original position, you are increasing the energy of the system, okay? So my question to you, I think most of you right now agree with me that if you look around the dislocation line, the atoms are shifted from their original position, right? So my question to you, do you see any difference? Can we classify the shifting around the dislocation? Is there any difference between what, if you look around the dislocation, do you think all of them, they shifted toward a certain direction? They have a certain type of shifting? Can we dig deeper and classify this different type of distortion?
They're going to the middle, kind of. The right hand going to the left and the left hand side going to the right.
Can you say it again, please?
They are kind of, the sides are going to the middle, kind of. They're centering to the middle.
Side is going to the middle. Okay. What else? Let's hear some other answers. What do you think is happening in terms of atomic position around the dislocation line? If you want to investigate what's happening in the name. تفضل.
We had at the beginning 6 columns, right? But below, down, we have 5. If we look up, there is 5 spaces. When there are 5 columns, we are trying to fill these spaces. That's what's happening. The change in
okay.
place.
Great. Good. It was good try, Sadiq. Can you? So that means you're saying we have more atom above the dislocation line compared to below the dislocation line. Is that true? Huh?
Yes.
Okay, great. So what do you think, ya Sadiq, if we have more atoms in the top compared to a perfect crystal, what do you think going to happen to those atoms? Do you think those atoms will be compressed, will be pulled away from each other? What do you think?
Can you repeat?
Okay.
I can't hear it.
Okay, because you said that you have more atoms in the top of the dislocation line, right?
Correct.
Compared to the perfect crystal, you have more atoms.
Correct.
So if you have more atoms, you think the bond between the atoms will be compressed or it will be stretched?
I think it will be compressed.
Compressed, right? Because in the same region you have now more atoms, right? So so this extra half plane of atom will try to push those atoms away, right? So there will be kind of compression in this region. So this region will be at the end will be under compressive for fields.
Yes.
Okay. Do you think this is also going to happen underneath it? Also, it will be compressive where you have missing atoms.
Yes, it should. It should يعني لا تكون نفس اللي فوق. السلوكيشن اللي فوق.
Formation.
Do you think they will be under compressive? So the atoms will come closer to each other, or think they will be a little bit far away from each other? Let's get some answers.
They will be stretched.
They will be stretched. Let's go back to Sami. Sami, what was your answer? Sorry, I did not get your answer.
Yes. If the dislocation continues, so it should be compressed.
So you think here the atoms will be compressed, so they will come closer to each other in this region?
Yes.
You think
if you compare it with the perfect lattice arrangement.
If you look at this bond that's connecting these two atoms, you think this bond is stretched or it's compressed compared to the perfect crystal?
I feel like it has the same spacing.
Okay.
Yeah. So I don't think it is compressed.
I think it's for you. It's difficult to answer the question, or it's for me. It's difficult to guide you because I'm saying almost far away from the dislocation, and this is a very important point. If you want to know the effect of the dislocation, you have to come closer to the dislocation. Okay. As you go far away from the dislocation, you don't see really the effect. Now, if you compare this one with the perfect, maybe you don't see the difference. What about if you come close and you look at this bond over here? Do you think this?
Yes, that's obvious. Yes.
Okay, great, good, Sami. So this is very important concept. The effect of the dislocation will be more around its surrounding area or region. As you go away from the dislocation, you might start to don't see the effect of the dislocation. Okay, great. So again, so what Sami said, if you come closer to the dislocation, you will get something here that is different than the one in the top. In the top, you get the atoms are compressed together because you have more atoms. The one at the bottom here, the atom under stretch, right? So they're under tensile. So in any dislocation, there will be some associated lattice strain. Lattice strain. That means the atoms are moved, shifted from their original position, right? So in perfect crystal, you're expecting to see a vertical line here, right? But because of the dislocation, right? So the atoms are shifted from the original position. And that shifting, okay, will result in some stresses. So in the top, you get compressive, okay, field. In the bottom of the dislocation, you get tensile. Okay, so any dislocation, any edge dislocation, you have compressive in the top. If you have upside down T, where the extra half plane of atom is in the top, okay, you got compressive in the top and you have tensile in the bottom. Okay, also you have shear stress around it. For the screw dislocation, you have only pure shear stress field. Okay, great. Now the question that we have, what's going to happen if you start to apply a shear stress? If you start to apply a shear stress, okay, you start to apply a shear stress. What do you think going to happen to this to the material? Okay, imagine you're applying a shear stress. They are going in the opposite direction. Okay, what do you think going to happen? What do you expect?
Edge dislocation will shift to the right.
Edge dislocation will shift to the right. Okay. In order for the edge dislocation to move, what do you need to do here inside the material?
Bones will be broken.
Wonderful, great. Thanks, Ali. So what Ali said, in order to move the dislocation as Faris said, now we have this extra half plane of atom. And also, let's call this, let's label it, huh? Let's call this A, B, C, D, right? So this is the top portion of B. This is the bottom portion of B, okay? In order for the dislocation to move, I need to break this bond over here between these two atoms, okay? All the bonds between these two atoms as you go inside the page need to be broken in order to allow the dislocation to move from one point to another. So what's going to happen? Let's now see as the time progresses, okay, and if you're still applying the shear stress, what's going to happen? So it's going to have the top portion of plane A will get connected to the bottom portion of B. And now the extra half plane of atom will be the top portion of
B.
Great. So if you want to draw it again, so this is the top portion of A, and it get connected to the bottom portion of B, XB. Let's call it XB. Huh? Okay, great. And now the extra half plane of atom B is here. Okay, so the dislocation moved, as far as said, from one point to another point within the material, and that movement required okay, required shear stress. But this is not accurate. Okay, please pay attention to this. When we apply shear stress, this location does not move. When we apply enough shear stress, that means the shear stress has to reach to a certain value. That value, if you reach it, then you will be able to break the bonds, as Ali said, you will break the bonds, and the dislocation will be able to move from one point to another. And if you keep applying this shear stress, what will happen? The dislocation will move from one point to another point, until it becomes to the surface of the specimen. And if you have a specimen that looks like this before you start any deformation, okay, this is the way it's going to look like after the deformation. Okay, so now the extra half plane of atom, it moved from inside the material all the way to the outside. Now, if one dislocation moved, that will result in a deformation equals to unit step of slip. Okay, unit step of slip. Okay, so that means the dislocation in each movement, it will move with a certain unit. Okay, and that unit will be clear, very clear, once the dislocation approach the, or extra half plane of atom approach the external surface. Great.
يعني هنا تحرك 5 units.
Sorry?
يعني هنا تحرك 5 units.
No, it moved a single unit. A single unit is called, oh yeah, totally yes. It moved five steps here in this point. But the total deformation that you see from outside will equal to the unit step of slip. Okay? Okay, good.
يعني هل نقول واحدة ولا هل نقول 5؟
Not one, only one. One. The dislocation moved, for example, in this case, let's say 4 steps or 5 steps, okay, in order to reach to the external surface. But the amount of deformation that you see from outside, from one dislocation, will equals to a single unit step of slip. Okay? Good? Because the dislocation was here, and then so we have extra plane of atoms here, and then when you continue applying the shear stress, the extra half plane of atom came to the surface, right? So the distance here is equal to unit step of slip, and in metallic material, okay, this is equals to the interatomic spacing between the atoms. Faris, you wanted to say something, please go ahead.
In C, in the figure C, can we say that the energy now is, the latest, the unit cell is equilibrium? The energy is like at the lowest level?
At the lowest level? I would prefer to delay the answer of this question toward the end of this chapter. Because what's gonna happen, we will see if you do more plastic deformation, are you increasing the amount of energy or decreasing the amount of energy? Okay.
Okay.
And yes. Also, just to answer you briefly, the answer is yes. If you get rid of the dislocation from inside the material, the answer is yes. Now look, the material becomes a little bit perfect, right? Because you get rid of this dislocation. So the dislocation gets outside of the material. So here material is more stable compared to before, right? Okay, great. Now let me get you back to the definition of plastic deformation. This is the stress strain curve. This is the engineering stress strain curve, right? We say that if you apply stress that is higher than sigma y, okay, and that stress will be the needed stress in order to initiate the plastic deformation. In other words, this is also will be the needed stress in order to reach to enough shear stress to move the dislocation internally, right? Okay, we will try to correlate between the sigma y and the applied shear stress on the dislocation, inshallah, next lecture, okay? Now the question, what is the definition of plastic deformation? Is it the movement of dislocation? The answer is no. It is the large movement of dislocation, as I said in the beginning of this class. So the definition of plastic deformation is the large movement of dislocation. Large movement of dislocations. So meaning you have to move more dislocation in order to see something from outside.